Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 9 on complex numbers. Now, complex numbers build on what we did in our last lesson on imaginary numbers. So if you haven't yet studied imaginary numbers, it is pretty important that you go back and either watch our Unit 9, Lesson 8, or make sure you've had some other exposure to the number I and to the imaginary number manipulations. That being said, let's jump right into complex numbers and figure out what they are. Complex numbers. All numbers fall into a very broad category known as complex numbers. Complex numbers can always be thought of as a combination of a real number with an imaginary number, and they will all have the form a plus bi, where both a and b are real numbers, but we call a the real part and b times I the imaginary part. All right? So, we can have numbers that are purely real, right? Numbers like -5, 11, 1/2, irrational numbers like pi. We can have numbers that are purely imaginary. They have a zero real component, like 7i, -2 times I, 3/4 times I, square root of 2 times I. And then we can have mixed real and imaginary numbers like 8 plus 2i, -3 plus 4i, 1/2 minus 8i, etc. All right? So all numbers can be thought of as complex. Now again, if you're dealing with just purely real numbers, all that means is that you have a zero imaginary component. You have 0 i's added on. And if you're talking about purely imaginary numbers, you can think of that as being sort of having 0 ones added on, right? There are no real numbers that are added on, all right? But we're going to be working today with mixed real and imaginary numbers, so truly complex numbers. All right, so let's first start talking about a little bit of arithmetic with complex numbers. And of course, you always want to start your arithmetic with adding and subtracting. Like real numbers, complex numbers may be added and subtracted. The key to these operations is that real components can combine with real components and imaginary with imaginary. And look, this is no different than if you were adding like 5 plus 2x to 7 minus 3x, all right? You want to almost treat the I like it's just a variable, all right? Let's take a look at exercise number 1. Find each of the following sums and differences. Letter A, -2 plus 7i plus 6 plus 2i. The beautiful thing about adding and subtracting complex numbers is that it works exactly the way you want it to. To begin with, right, let's take a look at letter A. To begin with, we can just take advantage of the associative property of addition and rewrite this as -2 plus 6 plus 7i plus 2i. All right? Now we can combine these two real components, -2 plus 6i, or sorry, -2 plus 6 is just 4, and then 7i plus 2i is 9i. Again, no different than if I had -2 plus 7x plus 6 plus 2x. It's identical to that, right? We're just sort of treating the I as a variable, as opposed to I being the square root of -1. So why don't you go ahead and try letter B? All right, again, very, very simple. We have 8 plus 4i plus 12 minus I. We can easily just group this with adding the two real numbers together and then adding the two imaginary numbers together. 8 plus 12 is 20. 4i plus -i is a positive 3i. So we just have 20 plus 3i. Real simple. Now, as always, subtraction is always a little bit more dicey than addition because when you subtract a binomial, you have to distribute the subtraction through the binomial. But again, this is nothing that you haven't done before, except without the I there, you may have had an X, a T, a Y, an N, or whatever. Let's take a look at letter C together. Here we have the complex number 5 plus 3i minus the complex number 2 minus 7i. And again, very simple. We could rewrite this initially without the parentheses as 5 plus 3i minus 2 plus 7i. In other words, subtracting that binomial means that we're going to sort of add the opposite, We can now again regroup so that we have 5 minus 2 plus 3i plus 7i. 5 minus 2 is 3. 3i plus 7i is 10i. And there we have it, right? Really quite easy. Why don't you go ahead and try letter D? All right, let's rewrite it first without the subtraction. We've got the complex number negative 3 plus 5i minus the complex number negative 8 plus 2i. So rewriting that, I'm going to have negative 3 plus 5i plus 8 minus 2i. I'm sure that many of you could then figure out the rest of this without first having to group things together. But just to be very clear, if I group the reals, negative 3 plus 8 plus 5i minus 2i. There we go. Kind of, sort of looks like 2i. Let's try to get it a little bit better there. Negative 3 plus 8, obviously 5, and 5i minus 2i is going to be 3i. There it is. So again, the beautiful thing about adding and subtracting complex numbers is it works precisely the way that you want it to. All right? And let's take a look at another one like this. This is a very kind of common multiple choice type scenario. Exercise number 2. If C is equal to the complex number 6 plus 2i and D is equal to the complex number negative 8 minus 5i, then which of the following represents 3 times C minus 2 times D? Now, complex numbers definitely work with the distributive property. In other words, if I've got a constant that's multiplying this particular complex number, I can distribute it across it. If I've got this constant multiplying D, I can distribute that across it. It's going to work just identical to all of that. So pause the video now and see if you can figure out the result here. All right, well, let's do it. So just doing a substitution, right, it looks like we're going to do 3 times 6 plus 2i minus 2 times negative 8 minus 5i. Distributing, we're going to get 18 plus 6i. We'll distribute that negative right away as well. Plus 16 plus 10i. Again, just kind of grouping the real terms together. That's going to be 18 plus 16 plus 6i plus 10i. And that's going to be 34 plus 16i. Apparently with a red dot on top. Uh-oh, what did I do wrong there? I don't see it. I've got 6i, I've got 10i. I think that there might just be a mistake in the That's right. The answer key. Yeah, yeah, that's right. It just doesn't happen to be on here. So there's a little bit of a typo here. My apologies. This should have been 34 plus 16i. So we've got choice 3. It's definitely not 12i. I don't know where that came from. But at least hopefully on your worksheet it actually says 34 plus 16i there. Just not in my display. It's none of the above. All right. Ah, the joys of doing math on the fly. Now let's talk about multiplying complex numbers. Adding and subtracting complex numbers is straightforward because the process is like combining algebraic expressions with like terms. The complex numbers are what are known as closed under addition and subtraction, i.e. when you add or subtract two complex numbers, the result is a complex number as well. But is multiplication closed? Let's see if we can answer that question by looking at exercise number 3. Find the following products. Write each of your answers as a complex number in the form a plus bi by using the fact that I squared is negative 1. All right, so it's very clear that when I add two complex numbers, I get a complex number. When I subtract them, I get a complex number. But it's a little bit weird that when you would multiply two complex numbers together, that you would also get a complex number. But in fact, you do because of this fact. And we looked at that a lot in our last lesson. I squared is equal to negative 1. That's going to be a very important fact as we move forward in this lesson. Every time you see an I squared, I want you to replace it with the number negative 1. So let's take a look at letter A together. We have 3 plus 5i times 7 plus 2i. Now, I want to attack this just as if I had 3 plus 5x times 7 plus 2x. You can do that with an area model, you can do it with double distribution, you can do it with the foiling method, which is the way I'm going to go about doing it. So let's go ahead and do letter A together. Here we go. So using FOIL, I've got first times first, 3 times 7, and that's going to be 21. Then I've got 3 times 2i, which is going to be 6i. Then I have 5i times 7, which is going to be 35i. And then I've got 5i times 2i, which is 10i squared. Now, if you were doing this problem and you were just had x's instead of i's, you would combine the 6i and the 35i. So let's do that. We'd have 41i. And then you'd kind of leave your answer probably like this, right? So if I had x's, this would be the end of it all. But, right, I squared, since I is the square root of -1, I squared is equal to -1, which means now I can write this as 21 plus 41i plus 10 times -1, which, let me extend the page a little bit, is going to be 21 plus 41i minus 10. Now the 21 and the -10 can combine, and that's going to give me 11 plus 41i. And notice, right, that is in the form of a complex number. A real number plus another real number times I. Now what I would encourage you to do from now on is if you see something like 10i squared, immediately replace it with -10. In other words, what that I squared is going to do is it's going to flip the sign on whatever the real number is that's multiplying it. So if I have 10i squared, I'm going to replace that with -10. If I had -5i squared, I would replace that with +5. All right? But besides that, besides replacing I squared with the number -1, what you're doing in these products is exactly what you did when you multiplied two binomials together. So let's get a little bit of practice on that. What I'd like you to do is take a shot at letter B on your own. Pause the video now and see if you can get the final answer in A plus BI form. All right, let's do it. So first, I've got -2 times 3, and that's going to be -6. Then I'll do outer. I have -2 times -2i, which will be positive 4i. I have inner, 6i times 3 is going to be positive 18i. And finally, I've got 6 times -2i, which will be -12i squared. All right, so -6 plus 22i, and then -12i squared, right? That's going to be -12 times -1. So that simply leaves me with positive 12. Now I can combine the 6 and the -6 and the positive 12 to give me positive 6 plus 22i. And if that's what you got, then you know how to multiply two complex numbers together, because, pun intended, it doesn't get any more complex than that. It really just doesn't, right? The only thing that's tricky at all is replacing the I squared with -1 and flipping the sign on that real number. So now, why don't you go ahead and try letter C as well on your own. All right, let's do it. So here we have the complex number 4 plus I times the complex number -5 minus 3i. Let's do it. So we've got 4 times -5 is -20. 4 times -3i is -12i. I times -5 will be -5i. And I times -3i will be -3i squared. All right, let's leave the -20 the way it is. Here we've got -17i, and here we're going to have positive 3 when we take that -3 and we multiply it by -1. The -20 and the positive 3 now will combine to be -17, and we end up having -17 minus 17i. All right, great. So, simple enough. Now we're going to continue to work with this idea of multiplying complex numbers together. You'll be happy about this. We will not be dividing complex numbers in this course. At least not if you're in your sort of typical Algebra 2 course. If you're maybe taking an honors level version of this course, your teacher might go ahead and show you how to divide two complex numbers. One of the really amazing things is that the division of complex numbers, unless you're dividing by 0, is also closed. In other words, dividing two complex numbers does in fact result in another complex number. But that's for a later course. All right, we're only going to be worried with adding, subtracting, and multiplying complex numbers together. Division kind of requires a little bit of a trick that we aren't going to go with in this course. All right, let's keep going. Number 4. Determine the result of the calculation below in simplest a plus bi form. All right, so here we have just simply a more complicated calculation. I'd like you to pause the video now and see if you can work through this one and find the final complex number that represents this calculation. All right, well, we kind of really have two things going on here, right? We've got this multiplication of these two binomials together, and that's what we were just doing, with this sort of simpler multiplication. All right, simpler, but it still matters. So let's tackle the first one. We've got to FOIL, so 5 times negative 3 is negative 15, 5 times I is 5i, 2 times negative 3i is negative 6i, and 2i times I is 2i squared. All right, now I might as well just do this one as well, but here I just have a single distribution. 4i times 2 is 8i, and 4i times 3 is 12i squared. All right, let's do a little bit of simplifying. I'll have negative 15. I could combine these, or I could wait. In fact, I could combine these and this. So I'd have 5i minus 6i, which would be, let me just do it one step at a time. Negative I. This I'm going to change into negative 2. I'll leave the 8i for the time being, and this I'll make into negative 12. Okay, let's take a look at all the real numbers. I've got negative 15, negative 2, and negative 12. That's going to be negative 17 plus negative 12, which is going to be negative 29. Then I've got, let me maybe circle my imaginary numbers so they're pretty clear. I've got my negative I and my positive 8i, which will combine to be a positive 7i. So negative 29 plus 7i. Fantastic. All right, so a little bit more of a complicated calculation, but one that you can certainly get through. Okay, but notice, right, all we're doing here is sort of manipulations we would have done anyway if we had treated I as a variable, okay, like x, y, n, c, doesn't matter. The biggest difference is every time we've seen an I squared, we've put in negative 1. Now let's talk about purely real or imaginary products. Because of how complex numbers form products, it is possible that the result of a complex product is a number that is purely real. In other words, it has a 0 imaginary component. Or a number that is purely imaginary because it's got a 0 real component. So let's play around with that idea a little bit in exercise number 5. Consider the more general product a plus bi times c plus di, where constants a, b, c, and d are all real numbers. Letter A. Show that the real component of this product will always be a times c minus b times d. All right. Well, why don't you pause the video now and play around with this. It's going to be pretty symbolic, but see what you can do. See if you can frame that in sort of the form of a complex number, meaning some kind of real component plus some kind of imaginary component times I. Pause the video now and play around with it a little bit algebraically. All right, well, let's do it. So I'm going to treat this exactly the way I was treating those other things. Right, I'm just going to FOIL it out. So I'm going to have a times c, all right, then I'll have plus a times d times I. Whoops, no, I just did that one. Plus b times c times I, plus a times d times I squared. Now remember, a, b, c, and d are all real numbers. so I can now replace this with negative a times d. What will I now have? Well, the portions that don't have, that's not right. Where did I get that? Oh, this wasn't a times d. That last one, I'm sorry, is b times di, so it's b times d squared. Like, I know that's not right. There we go, b times d. So the real portions, the portions that have no i's attached to them now are ac times bd, and I'll put that in parentheses. And now here are the two components that have got an I in them. So I'm going to write those, I'm going to factor that I out as a times d plus b times c times I. Wow. And again, my apologies here. When I FOILed this out, I made a mistake on the L term, literally the last term, which should have been bi times di, giving me b times d times I squared. Turning that I squared into a -1 gives me just minus b times d. Therefore, a times c minus b times d, right, is the real component, and a times d plus b times c then is the imaginary component, right? Great. So we did it, and maybe I should just really be very clear. Here is the real component. All right. So let's take a look at letter B. Show that the product of 2 plus 3i and 4 minus 6i results in a purely real number. Awesome. Well, what I'd like you to do is actually just do that product. Do 2 plus 3i times 4 minus 6i and see what you get. All right, well, let's go through it. I want to do 2 plus 3i times 4 minus 6i. Let's see if I can actually do it correctly. I've got 2 times 4, which is 8, right? Then I've got 2 times negative 6i, which is negative 12i. Then I've got 3i times 4, which is positive 12i. And then I've got 3i times negative 6i, which would be negative 18i squared, which is going to be 8. And notice I have negative 12i, positive 12i cancel. That's going to turn into 18. And all of that is then 26. And that is a purely real number. Right? And the reason it's purely real is because I had these opposite imaginary components. I literally have 0i. Negative 12i, positive 12i cancel, and I'm just left with 26. And we could phrase that as 26 plus 0i. That'd be fine. But of course, 0 i's is just 0. So we have 26. Now let's look at the last part of this problem, letter C. Under what conditions will the product of two complex numbers always be a purely imaginary number? Check by generating a pair of complex numbers that have this type of product. Well, here's the key, right? Take a look at this very general product, right? We know right now that a plus bi times c plus di is equal to a times c minus b times d, that real component, plus a times d plus b times c times I. So how will this ever be completely imaginary? Pause the video now and think about that for a moment. Well, this is going to be, let me change to red, purely imaginary if all of this is equal to 0, right? So in other words, we're going to have a purely imaginary number as long as something very special happens, right? As long as a times c minus b times d is equal to 0, or better yet, as long as ac is equal to bd, right? Now, you know, what are that? Well, AC, right, is the product of these two real components. BD is the product of these two real portions of that sort of imaginary component, right? As long as those two products are equal, well, then I'm going to have a purely imaginary number, right? So it says, well, check by generating a pair of complex numbers that have this type of product. All right, well, there's a lot of different ways I could do it. I could make A and B equal and C and D equal, but here's kind of a cool one. And again, there's a million different ways to do this. I could make A equal to D and C equal to B. That would work, all right? Or I could even go a little bit cooler. I could say, well, let me say that A was equal to 3, and let's say C was equal to 6, right? That would make their product equal to 18. So like, let's say B was equal to 2 and D was equal to 9. And that would make their product equal to 18. So let's see if this will work. Let's say if we go up here and we do 3 plus 2i times 6 plus 9i, let's see if we get a purely imaginary product. All right, so 3 plus 2i times 6 plus 9i. Let me extend the page a little bit. Come on. There we go. And again, there's a lot probably easier ways to do it. Let me bring this down a little bit. All right. 3 times 6, that's going to be 18, right? Then I'll do 3 times 9i, that'll be 27i. Then I'll do 2i times 6, that'll be 12i. And then let me do 2i times 9i, and that's going to be 18i squared. And you can probably already see why this is going to be, before we even finish it, why it's going to be purely imaginary. Here I've got 18, and 18i squared is going to become a negative 18, and those two real components are going to cancel. So I'll have 18 plus 39i minus 18. Those two cancel, and I'm left with 39i. And again, don't get me wrong, right? If you made A and C equal, if you made A and B equal and C and D equal, it would also work. So if I had something like 2 plus 2i times 3 plus 3i, that would also give me a completely imaginary result. I just wanted to do one where like they weren't all that easy. You know, it was a little bit more complex. I did it again. That time it really wasn't intentional. Exercise number 6. Which of the following products would be a purely real number? All right. Now, one way to do this, to get a purely real number, is to literally find every one of these products. Every one of them. But for a moment, think back to this, right? And maybe even back before that. Every time, so let's actually go one more back. Let's go all the way back here, right? If I want a purely real number, then what's got to happen is that these quantities, the O and the I in foiling, if you will, have to cancel. To have a purely real number, the O and the I, when we FOIL, have to cancel. So, I'd like you to try to avoid doing the entire product and just think about when you do this, when you FOIL, right, what will need to happen to get those to sort of cancel each other. Because if you can do that, then you will end up with a purely real number. Pause the video now and see if you can just play around with that. Well, let's take a look at the first one, right? The O and the I here would be negative 4i and 6i, and that would be 2i, and therefore it would have an imaginary component. In this particular one, right, I would have negative 12i and negative 2i, and that would be negative 14i, which would have an imaginary component. In this one, I would have negative 10i and positive 10i. Oh, and those would cancel and give me 0i, which means this would be a purely real product. So choice 3. And that's really all about knowing what gives you the imaginary component of a complex product and what gives you the real component of a complex product. All right, let's summarize. There is a lot of arithmetic that one can do with complex numbers. In fact, basically any kind of arithmetic that you can do with real numbers, you can do with complex numbers as well. But that is far outside of the scope of this course. In this course, we're really only going to be looking at adding and subtracting complex numbers and multiplying them as well. All right? The beautiful thing about adding and subtracting complex numbers is it works exactly like combining like terms. And multiplying complex numbers, which is a little bit more difficult, a little bit more complicated, right, still works just like multiplying two binomials together. The big difference is when you get that I squared, you replace it with a -1, which simply changes the sign of its real coefficient. That's all it really does. And you ultimately still get a complex number. All right, well, I'm hoping that you work a lot more with complex numbers if you take pre-calculus next year. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.